In 2012, a 40-year-old spacecraft crossed a boundary no human-made object had ever crossed before, and the moment it did, it recorded something that flatly contradicted what physicists had spent decades predicting. Not a small discrepancy, not a rounding error, a measurement so far outside expectations that some scientists spent years afterward questioning whether the spacecraft had actually left the solar system at all. This is the story of Voyager 1's magnetic field measurement at the edge of interstellar space, a single piece of data that forced an entire community of heliophysicists to rethink how the boundary of our own solar system actually works, and one that's still shaping new research today, right as Voyager 1 approaches another historic milestone of its own. Stick around, because the way this mystery eventually got solved is a genuinely satisfying piece of scientific detective work. And if you want to catch every update on Voyager as it keeps making history, go ahead and hit follow before we get into it. To understand why this measurement caused so much confusion, you first need to understand what scientists expected to happen the moment Voyager 1 left the solar system, and why they were so confident about it. Our entire solar system sits inside a massive protective bubble called the Heliosphere, inflated by the constant outward flow of charged particles streaming from the sun, known as the solar wind. That bubble extends billions of miles past the orbit of Pluto, and for decades, physicists modeled it the way you might model any other bubble, pushing outward into a surrounding medium, with a fairly distinct boundary separating what's inside from what's outside. Beyond that boundary lies interstellar space, filled with material and magnetic fields that originate from other stars scattered throughout the galaxy, not from our own sun. One of the clearest predicted signatures of actually crossing that boundary involved the direction of the magnetic field itself. Inside the heliosphere, the sun's own magnetic field dominates everything, stretched outward and shaped by the solar wind into a specific, well-understood orientation. Outside the heliosphere, in true interstellar space, the ambient magnetic field is generated by entirely different sources, the collective influence of countless other stars, and the broader structure of the galaxy itself, and physicists expected that field to point in a noticeably different direction. So the reasoning was straightforward. If Voyager 1 ever actually crossed into interstellar space, its onboard magnetometer should detect a dramatic, unmistakable shift in the direction of the magnetic field, essentially the moment the spacecraft stepped out of the sun's magnetic influence and into the galaxies. In August of 2012, Voyager 1 sent back data showing several signs consistent with leaving the heliosphere. The number of charged solar particles around the spacecraft suddenly dropped by roughly 1,000-fold, while the number of fast-moving cosmic rays originating from outside the solar system spiked upward by about 9%. Both of those readings lined up exactly with what scientists expected to see at the moment of departure. But the magnetic field data told a completely different story. Instead of swinging dramatically to a new orientation the way every model predicted, the magnetic field measured by Voyager 1 barely changed direction at all. It got noticeably stronger, consistent with compression at the boundary, but it kept pointing in essentially the same direction it had been pointing while still deep inside the heliosphere. For the scientists working on the mission, this was genuinely unsettling. Len Berlage, one of the co-investigators on Voyager's magnetometer instrument, later described their reaction bluntly, calling it a real shock to the entire team, because everyone had assumed that leaving a completely different magnetic environment behind would obviously come with drastic directional changes. Some researchers seized on that missing signature as reason to doubt the crossing had happened at all, arguing that Voyager 1 might still be embedded somewhere within the outer edge of the heliosphere, just in an unusual transitional pocket, rather than genuinely out in interstellar space. It created a strange, uncomfortable situation. Two of the three expected signatures lined up perfectly. The third, arguably the most fundamental one, seemed to be missing entirely. NASA did eventually confirm, using additional data gathered from a separate coronal mass ejection event that reached Voyager 1 the following year, that the spacecraft really had crossed into interstellar space back in August 2012. Researchers were able to measure the density of the plasma surrounding the spacecraft by observing how it oscillated in response to the shockwave from that solar eruption, and the density they found was dramatically higher than anything recorded inside the heliosphere, consistent with the far denser environment of interstellar space. That settled the basic question of whether the crossing happened. But it didn't resolve the deeper mystery of why the magnetic field refused to behave the way every model said it should. That mystery lingered for years, and it wasn't just an academic curiosity. It struck at something fairly fundamental about how physicists understood the structure separating our solar system from the rest of the galaxy. If the magnetic field doesn't shift direction the way theory predicted, that suggests the boundary itself isn't the kind of clean, sharply defined edge scientists had been picturing. It hints at something messier, some kind of interaction or blending happening right at the interface between the sun's magnetic influence and the galaxies, rather than a simple, well-defined wall separating the two. The breakthrough eventually came from a research team led by astrophysicist Nathan Schwadron at the University of New Hampshire, published in the Astrophysical Journal Letters. But rather than relying solely on Voyager 1's own measurements, Schwadron and his colleagues combined data from 4 completely different sources, including NASA's Interstellar Boundary Explorer mission, known as IBEX, which had discovered a strange ribbon-shaped feature of energetic neutral atoms back in 2009, thought to trace the direction of the true, undisturbed interstellar magnetic field. By triangulating Voyager 1's readings against IBEX's ribbon, along with additional data from the Ulysses and SOHO spacecraft, the team found something remarkable. All of these independent datasets, collected over roughly 25 years using completely different instruments and techniques, were pointing toward the exact same underlying direction for the true interstellar magnetic field. What that meant was that Voyager 1's confusing magnetic field readings weren't actually wrong or inconsistent. They were revealing something physicists hadn't fully appreciated about the region right around the Heliopause itself. Schwadron described it using a simple analogy, comparing the interstellar magnetic field to a rubber band stretched around a beach ball. As that band gets deflected around the curved surface of the ball, it bends and drapes around the obstacle rather than staying perfectly straight. In the same way, the interstellar magnetic field doesn't slam directly into the heliosphere and switch directions. Instantly, at some sharp boundary line, it drapes around the sun's magnetic bubble, gradually bending and reorienting itself as it wraps around the heliosphere's shape, which means a spacecraft crossing that boundary experiences a slow, gradual rotation in field direction rather than a single dramatic snap. The study found that Voyager 1's magnetic field readings had, in fact, been slowly and steadily turning ever since the spacecraft crossed into interstellar space, just far more gradually than anyone had originally anticipated. Later research added even more nuance to the picture. A team led by astrophysicist Merav Ofer pointed out that the heliopause isn't the static, rigid boundary early models assumed it to be. Interstellar. Magnetic field lines can pile up and drape around the heliosphere in complex ways, sometimes twisting, sometimes even breaking apart and reconnecting in new orientations entirely, a process called magnetic reconnection. Some of these field lines may even form narrow tunnels called flux tubes that allow small amounts of solar particles to leak directly out into interstellar space through the boundary, blurring the line between what counts as inside the heliosphere and what counts as outside it. Ofer and her colleagues later reflected that, in hindsight, they probably shouldn't have been so surprised by the magnetic complexity Voyager 1 revealed, given just how dynamic and structurally messy a boundary like this was always likely to be. So the sharp, clean picture of the heliopause that dominated textbooks and models before 2012, a simple boundary where the sun's magnetic influence ends and the galaxy's magnetic influence instantly begins, turned out to be far too simple. Voyager 1's confusing, seemingly contradictory readings forced an entire field of physicists to replace that clean mental model with something much closer to reality. A soft, draped, gradually blending boundary shaped by complex interactions between two overlapping magnetic environments, rather than a hard edge you cross in a single instant. This entire episode is a genuinely elegant example of how science actually progresses. It wasn't that Voyager 1's instruments malfunctioned or that the spacecraft's data was somehow flawed. It was that reality turned out to be more complicated and more interesting than the simplified models scientists had been using to predict it. And it took years of painstaking work, combining data from multiple independent missions using completely different measurement techniques to fully understand why a single decades-old spacecraft kept returning numbers that didn't match anyone's expectations. Remarkably, Voyager 1 is still out there right now, still transmitting, and it's approaching another milestone that will make communicating with it even stranger than it already is. Later this year, on November 18th, 2026, Voyager 1 is expected to cross a distance of exactly 1 light day from Earth, a point roughly 16 billion miles away, where a radio signal traveling at the speed of light takes a full 24 hours just to reach the spacecraft, and another full day for any response to make its way back. Mission engineers have described the process bluntly. Send a command on a Monday, and you won't know how the spacecraft responded. Until Wednesday. NASA's Voyager project manager, Susie Dodd, has compared the mission's ongoing measurements of the heliopause to studying the shoreline of an ocean, watching the ripples, waves, and changing conditions grow more subtle and more stable the farther the spacecraft travels from that boundary, mapping out exactly how the sun's influence fades with distance in a way no other instrument has ever been positioned to observe. Voyager 1 is running on a steadily decaying nuclear power source, and NASA engineers have already had to shut down several of its scientific instruments over the past few years just to keep the spacecraft's most essential systems running. Officials have suggested the mission could realistically continue for another 2 to 5 years before power finally runs too low to keep any instruments functioning at all. That means the window for gathering more of this kind of data, more insight into exactly how the boundary between our solar system and the wider galaxy actually behaves, is narrowing every single year. What makes the magnetic field story worth revisiting right now isn't just that it's a fascinating piece of scientific history. It's a reminder of exactly what's at stake as this aging spacecraft continues its slow march deeper into interstellar space. Every additional year Voyager 1 keeps transmitting is another year of direct, in-place measurements from an environment humanity has never been able to study any other way. An actual physical presence sitting in the space between stars, rather than a model or a simulation built from indirect evidence. The magnetic field mystery took years to fully unravel, using data patched together from multiple missions launched decades apart. There's no telling what other confusing, seemingly contradictory readings this remarkable spacecraft might still be sending back, quietly waiting for the right combination of future data and future insight to finally make sense of them. If a story like this, a 40-year-old spacecraft accidentally rewriting scientists' understanding of where our solar system actually ends, is the kind of thing that genuinely fascinates you, go ahead and subscribe. Drop a comment letting me know what you think Voyager 1 might still have left to teach us, and stick around, because there's a very real chance this remarkable little spacecraft still has more surprises waiting in its data.